every piece of infrastructure will start resembling what we have here with Lakebase. At the minimum, like every stateful system, you got to have the ability to create a staging environment, a branch of what you have, and give the permission to agents to make mistakes.
This is It's About Data, episode 76. We're continuing our conversation with Nikita Shamgunov on Lakebase and its implications for software engineering and architecture. All right, Nikita, last time we talked about the architecture, this novel architecture of Neon, now Lakebase, and the fact that you're separating compute and storage, you're using object storage, you're doing a lot of things that we used to see in the hybrid OLTP, OLAP world. As a data engineer, so I've spent a lot less time working at like real low level inside of Postgres, which you've spent a lot of time on that. But I do have some questions about this. So what is the role? You're a software developer, you're vibe coding, or maybe we call it just like assisted coding or something like this, and you're developing these new apps. How do we prevent, let's call it spaghetti data? How do we prevent just an explosion of messy schemas and such? Because this has been a problem for a long time. If you've ever dealt with ORM, it generates these crazy schemas, and it seems like there is a risk here that we're just going to get an explosion of really messy data. So what's the role of the software developer in sort of shepherding these agents to make sure that the data doesn't turn into a huge, nasty mess?
Well, this is a good question. So oftentimes, even with humans, you will have some sort of schema drift that you start and everything is nice and clean. New requirements come in, you implement a bunch of features. Your team implements a bunch of features. Now it's teamwork, and therefore things get more complex and messy over time, and then everything slows down. Your application performance may slow down. Your productivity of your team may slow down due to the rapid increase of complexity. So I think this problem is just going to arrive sooner because the clock speed is faster, right? And in assistant coding, people make changes with AI. And we are seeing more and more drive towards fully autonomous systems.
Yeah.
The thing that counteracts this are the following. And we kind of discovered them as software engineering teams built with humans, not a long time ago, but like we know what to do, right? There's checks and balances here. They are called CI/CD, or software development life cycles. They're called code review. They're called best practices. They're called design patterns. They're also, they're called having technical lead or a senior engineer in the team that polices this in a good sense of the word policing. But there are a couple things that will help us in the future. I think. And by the way, we made a good amount of progress in ORMs as well. So ORMs generate less spaghetti code generally. I think the whole automation of the CI/CD process, as well as the quality of AI-generated code, is rapidly going up. And what I think new models just produce less slop, to be honest.
Interesting.
I think, we were at the level of an intern, now junior engineer, now senior engineer. The understanding of the code, understanding of the project by those models is a much, much higher quality.
Plus, there's another really interesting feature, though, and I think which you guys introduced here, which is to avoid some of this duplication, which is your ability to branch and use basically a very developer-centric type of approach with CI/CD, but being able to branch so you're not exactly.
I think the higher of it is model quality, to be honest.
Yeah.
Now, then there's all this check and balances in the CI/CD loop, in like inner loop of software engineering, and of course, every part of that loop will be driven by AI. Right? Because, if there's one thing we software engineers are good at doing is automating stuff. We now have the tool to automate CI/CD. We will do it. And we're doing this. And we're certainly doing it at Databricks, and every progressive company is doing that. Now, in order for that loop to run well, infrastructure needs to have enough primitives to support this. One of the most basic primitives of the past was the ability to Git branch, right? So Git has branches and GitHub has pull requests. So that was the workflow that was driving CI/CD and GitHub Actions for testing, right? Those are the main ingredients of your software development lifecycle. Here we're introducing branches for stateful systems, which was always lacking. And we have this ugly staging environments that were shared across team of developers. We have daily uploads of data with some sort of sanitization and masking PII happening from your production system. And remember, nobody is going to give access to production systems, not to your analytical system, not to your development team. Like that's just not happening, right? So we're extracting data, we're putting in the staging system. Staging system is shared to your team of developers. So if I want to change the schema and you want to change the schema in the same live system, we conflict. And that's why the introduction of branching, which is only possible because we rebuilt our storage, which is only possible because we built it on the object store. Well, kind of implementation detail of our storage implementation. Yeah. So all of that together starts stacking as like Lego bricks for this architecture. Now, the other wonderful thing to be connected to Databricks and the lake is the ability to capture all the telemetry that's hitting the system in the lake. And then when agents make changes in the system, you can give that information that we've captured, the telemetry information and logs to agents to go and build the next iteration. So now from the logs, you know what your slow queries are. From the logs, you know inefficiencies in your query plans. From the logs, you know all the latencies that you potentially might want to optimize. And of course, from the logs, you can very quickly act on all sorts of security breaches and vulnerabilities. So I think in the name of software development lifecycle automation, every piece of infrastructure will start resembling what we have here with Lakebase. At the minimum, like every stateful system, which you access either as infrastructure or as an API system, but you got to have the ability to create a staging environment, a branch of what you have, and give the permission to agents to make mistakes.
I have a couple questions with regard to basically referred to in our first session about your use of object storage. And of course, it's not new, for analytic databases, for data warehouses. It is pretty unusual, for transaction systems, where essentially, where basically you have a lot of the updates, you have a lot of the CRUD activity that object storage was not designed for.
No.
And obviously you've put a cache layer above that, but I get a sense of that it's deeper than that. So can you basically talk to us in terms of both the architectural ramifications of going to object storage, the economic ramifications, and the ramifications in terms of basically the operational scenarios, the use cases?
Yeah. So I think you got to flip your thinking from hey, I'm running one database to I'm running a gigantic fleet of millions of instances, and those millions of instances are sharing their storage. And that storage, let's not talk about if it's object store or not object store just yet. It's some sort of storage that accessible to your to each individual compute instance, which is Postgres, over some sort of API. And the important thing is a multi-tenant storage, right? Then from there, what properties you want to have for this storage? We already talked about branching. There's also performance characteristics to this storage. So the ability to write a durable transaction should be fast and reliable, right? And therefore, it needs to have an implementation of some sort of consensus algorithm, such as Paxos or Ruft. So if a transaction arrives to my storage, you need to, and you tell Postgres, so it's like, hey, I got it, it's in. It's better be in. You know what I mean? Like it's better to be durable by that time. And then if you read a piece of data, that data needs to be served to a Postgres instance with minimum latency possible. It is incredibly important that none for in a working state, right, when the system is up and running and serving transactions, that our working set never has object store on the transaction read or write. So all interaction with the object store are asynchronous, meaning I send a transaction to my storage, and it's persisted in a super low latency in NVMe in a super low latency durable medium very, very quickly. I acknowledge the receive of that transaction, that I asynchronously move that transaction into the object store. Now, why do you need an object store at all? Well, you're running millions of databases. Cost actually matters. As a matter of fact, OLTP market generally is very price sensitive. If you, there are numerous examples in various attempts from small and large companies that blew up the cost of their system. And when they go to their customers and deliver their product in the cloud, it's not price competitive with some other systems provided either by us or by hyperscalers, by whoever else. But if you like, it's very easy to like 10x the cost and not notice it. And then
Yes,
like
it
you can't
is.
compete on price. Like you priced out.
Yeah.
So now when you run a very large fleet, and our larger customers, they spin up thousands of databases per day actually. That cost equation really matters. So now it's hard enough to deliver on price. It's hard enough to deliver on performance. But what's important is to deliver on price performance. And what's important is to have an architecture that can be driven to give you extremely good performance. We actually exceed the performance of a Postgres instance on an NVMe, believe it or not. Like it sounds kind of strange. Like you separated storage, that should make things slower. You put storage on an object store, that should make things even slower. But overall, the throughput of our system actually increased. How is that even possible? Well, it is possible is because remote storage is low latency. And it is possible is because with deep understanding of database systems, you can move some of the operations that the database system does to maintain durability and consistency into storage, and now kind of spread that across a large fleet of machines that implement storage. And so we're roughly 3 times faster than Postgres that's running on NVMe.
So let me ask this. I mean, before the show started, you Databricks wanted to talk a bit about uptake, and it sounds like the uptake at Neom was incredible of this technology, and now the uptake since GA at Databricks of Lakebase has been incredible. Hybrid OLAP OLTP is nothing new. That's been around for a while. It sounds like you bring some unique capabilities to that. But from your perspective, is there one unique ingredient that's really driven the uptake? Because frankly, the uptake of past hybrid systems has not been great. You had cost issues, you've had complexity issues. Is it agents or is it something else? Like what's the ingredient that's really driving this uptake this time?
Well, my thinking changed. So I built single storage hybrid system. It crossed 100 million ARR. It was an incredibly long time to get there, and eventually acquired by private equity. So, and that confirms your statement that the uptake of hybrid systems historically have not been great. However, and that's where my thinking changed. It changed from having a hybrid system that supports operational and analytical workloads in one engine to best-in-class engine for analytics, which is Spark, DB SQL, and further improvements in the engines, and then best-in-class OLTP system, which is Postgres. And OLTP is so developer-driven, and developers already voted they want Postgres. Integrated at the storage level.
Mm-hmm.
So from the practitioner, from the developer, from data engineer, they're getting best in class engine that they know and trust. But from the, okay, well, those engines, they inevitably needs to be connected for a variety of reasons. They need to be connected for the reasons we run ETL today. They need to be connected because a lot of the things, in like AI and ML realm, computed in the lake, and then that data needs to be served and therefore need to be moved into LTP. So those systems are inherently connected. And so how do we make that connectivity as seamless as possible and as performant as possible? And if those things are connected by the storage fabric underneath, which we call the lake, we now can move data freely between those systems, and we can also access data in place inside those systems. So I think that's like the biggest architectural evolution from having one hybrid system that does it all to having two best-in-class systems that are already proven but integrated underneath with the storage fabric. So now, when we talk about customer momentum, a lot of customers of Databricks start on the lake, and then because they have data there and move it into Lakebase. And a lot of customers of Neon start with Neon because they build an application, and then they need to move data in the lake, and Lakebase kind of like automatically does it there. So that's why we're approaching this from both ends.
Well, anyway, it sounds to me like your message here, and again, I think we've only scratched the surface of the water here, is go jump in the lake, whether it be from the analytics side and now also from the transaction side. Anyway, Nikita, I very much appreciate you taking the time to share your insights with us and to share kind of the direction of where Lakebase is going. Well, we look forward to having another discussion with you, say a year down the line, just to see, like, especially as as agentic adoption ramps up, how this is panning out. Nikita, thanks for taking the time.
Of course. Thank you so much.
Okay.
Thank you for having me.
Thank you.
Bye-bye.